Hi everybody, welcome back. In this video we're going to cover the topic of binary classification. In machine learning, classification refers to the predictive modeling problem of identifying which of a set of classes an observation belongs to. In the figure below we're showing a hypothetical data set that represents two classes. And here we've color-coded the classes as red and blue, but this is only for visualization purposes. The classes themselves are characterized by two features, x1 and x2. And our task is to define a model that will predict the correct class based on the value of the two input features. And so as shown in the figure below, the model that we develop will lead to a linear decision boundary. So rather than predicting a real valued number as we did with regression, our goal is to predict the correct class label based on the feature data. So before we dive into the details, let's go ahead and preview the topics that we're going to cover in this notebook. In this first section, we're going to introduce the mathematical foundation for binary classification, and we'll show that it's closely related to linear regression with the key difference that we'll be using a sigmoid activation function. And we'll show how this leads to the development of a binary cross-entropy loss function. We'll then show how the network architecture is very similar to the previous architecture we studied in linear regression. And to illustrate this with an example, we're going to create a synthetic data set that contains two classes, where each class has two features. Then, having prepared the data, we'll model the architecture in Keras using the standard workflow as we've done before. And then after implementing and training the model using binary cross-entropy loss, you can see that we have a training loss that looks well-behaved and a resulting classification accuracy that seems just about right based on the data we showed above. In this next section here, we'll show how we can use the predict method to first compute a score that can then be thresholded to determine the class assignment. And then in the final section of this notebook, we're going to take a look at several diagnostics that can be really helpful in getting a better appreciation for the underlying algorithms. First, we'll show that we can use the weights from the network to compute a value for the activation function for every training sample, which gives us a little more insight as to how the approach works for classification. We'll also learn how to plot the linear decision boundary. And finally, we'll demonstrate how to compute a confusion matrix that produces a very convenient summary of the classification results. So let's go ahead and dive in, and we'll get started with a description of the mathematical model for classification. Recall that for linear regression, the predicted output from the network was simply the weighted sum of the input features, which produced a single real-valued number known as y prime. So this was the final output of the network. In order to turn this into a classification problem, we can pass this weighted sum of inputs, which we'll now call z, into a sigmoid activation function shown below. The value returned from the sigmoid function will now be a predicted score y prime in the range from 0 to 1 that we can use for classification. And we can think of this value as the probability associated with the input belonging to one of the two classes. Specifically, let's assume that the output of the activation function is the probability that y equals 1 given x. In other words, it's the probability that the true label for the class is 1 given the input x. Assuming that, we can also interpret the probability that y equals 0 given x as being equal to 1 minus y prime, since there's only two classes to consider. So just to reiterate, y represents the ground truth for the class label, and y prime represents the probability that the input is associated with class 1. So y is either 0 or 1, and y prime is a value in the range between 0 and 1. And conveniently, these two expressions can be combined into a single equation as shown below, which can easily be confirmed by setting y equal to 0 and y equal to 1 to show that they simplify to the first two equations. We'll see further below in this notebook how this actually works, but let's continue on and consider how we might learn the parameters for such a model, which is going to lead us to the development of a new loss function. So let's start with the idea that our goal is to maximize the probability of y given x. If we then take the log of both sides of this equation, that won't affect the optimization, but will make things mathematically much more convenient for us. And then in order to turn this into a minimization problem, we can simply take the negative of this expression, and this leads us to the binary cross-entropy loss function shown below. And recall that y prime in this case is the output of the sigmoid function, where z is equal to theta transpose x. And then finally, in order to make the prediction for the correct class, we simply need to assign the class label to 1 if the output of the activation function is greater than 0.5, and assign the class label to 0 if it's below that threshold. And you can convince yourself that this makes sense by studying the table below, in which we've provided some numerical examples. Let's now take a look at the model architecture for binary classification as shown in the figure below. The only difference in this architecture and the previous architecture for linear regression is that we're now using a sigmoid activation function rather than a linear activation function. And in this case, we're using a loss function, which is binary cross entropy, as opposed to mean squared error or mean absolute error loss. It's also worth noting here that we can perform binary classification regardless of the number of features. So in this case, we happen to have 2 features, but we could also perform classification with any number of input features. In this next section here, we're going to generate some synthetic data to work with using the following convenience function, which is going to create a normal distribution of data points for 2 different classes. And if you're interested in experimenting with this a little bit yourself, you can simply change the default statistics in the definition of this function, or call the function with the optional arguments to specify the statistics for each class. So next we're going to go ahead and call this function and plot the data points so we can see what we're working with. As shown in the plot below, we clearly have 2 distinct groups, but we can also see a small percentage of points that are clearly not separable with a linear boundary. And so in this case, we'd be expecting a model accuracy on this data set to be less than 100%. So now that we've generated some feature data for each of the classes, we also need to create the associated ground truth labels for each class. And that's what this next function does. It takes the feature data for each class and then builds the associated class labels. And notice that in this notebook, we're not really concerned with validation or testing. We're simply trying to demonstrate the basic concepts for creating a binary classifier. So throughout this notebook, we're simply going to be working with the training data. And so now at this point, we're ready to model all of this in Keras, and we'll be using the workflow indicated below as we have before. We'll begin by first defining a normalization layer for the training data. And notice that we're using an input shape of 2, and that we're setting the axis to be 1, which is the axis associated with the features. Next, we're going to create a model using the sequential API, and we're going to add the normalization layer. And then we're going to add a dense layer with an input shape of 2 and a sigmoid activation function. And notice that there's 5 non-trainable parameters associated with the normalization layer, which contain the mean and the standard deviation for each of the features, plus the number of data points. And in the dense layer, we have 3 trainable parameters, which are the weights for each of the input features, and then a single bias term. So now we're ready to compile and train the model, and notice here that we're specifying the loss function as binary cross entropy. And then we're going to train the model for 100 epochs. And as you can see in the training curve below, the loss comes down fairly quickly and then levels off after about 80 to 100 epochs. And next we can evaluate the model, and we'll do that first by calling the evaluate function, passing in the training data, both the features and the labels. And you can see there that the final accuracy of the model is about 97%. And then we can also plot that accuracy as shown in the plot below. So now that we've trained and evaluated the model, we can also use the model to make some individual predictions, and that's what we're accomplishing in this next section of code here. You can see that we're calling the predict method for 2 different sets of input features, and that function now returns for us the predicted score, which is the output of the activation function. And then recall from our earlier discussion, in order to make the class assignments, we need to compare the predicted score to a threshold of 0.5. And for that purpose, we're defining this convenience function, which takes the predicted score as the input and returns the class label. And as you can see in the console output below, the results for the 2 test cases we specified. And to make this just a little more concrete, let's take a closer look at the role of the activation function that leads to the predicted scores and therefore the class assignments. To do this, we're first going to define 2 very short convenience functions, one that computes wx plus b, and the other one that takes that computation and computes the output of the activation function, which we'll plot further below. In order to use these functions, we're going to need to retrieve the weights from the model. And as we've shown before, we can use the getWeights method to retrieve both the weights and the bias term. And then because we used a normalization layer when we trained the model, we also need to back out the normalization computations so that we can correctly interpret the weights for this purpose. But again, we just want to emphasize that this is only for diagnostic purposes and is not required to actually use the model to make predictions. It's just something that can be very helpful to gain some additional insight when learning this material. And so for those of you that might be interested, it would be a really great exercise for you to convince yourself that these conversions make sense. So now that we've unnormalized the weights, we can go ahead and call both of these functions, and that's what we're doing in this next section of code below. Notice that we're calling each of these functions for the two different classes separately so that we can color code the ground truth for the classes when we plot the results below. And now you can get a very clear picture as to why the classification algorithm works. For example, any points that are above a threshold of 0.5 are associated with class 1, otherwise they're associated with class 0. And of course, you can see there's a small number of points that are misclassified near the boundary, which is due to the fact that the data set is not linearly separable. And that now leads us to the next section in which we're going to learn how to plot the decision boundary. In this function that we've defined here, we're first plotting all the data points color-coded by their true class. And then in order to plot the decision boundary, recall that the input to the activation function is the weighted sum of the inputs plus a bias term, which in this case is simply W1x1 plus W2x2 plus B. And so if we rearrange that equation and solve for x2, you can see that we get the familiar form for an equation of a line. And therefore, in order to plot this line, we simply need to generate some values for x1 over the range of interest, and then compute the value of x2 based on the weights of our trained model. And as you can see in the results below, we get a linear boundary that separates the two classes very nicely. Notice that there's only one member of class 1, which is red, that's misclassified as class 0, and that there's several members from class 0 that are misclassified as class 1. And this now leads us to the final section of the notebook in which we're going to compute what's known as a confusion matrix for a binary classification problem. If you're not already familiar with what a confusion matrix is, it's simply a way to summarize the results of a classification algorithm for a set of data. So in this example, we're going to compute a confusion matrix for binary classification. And in the bullet points below, we're showing the four possible cases known as true positive, true negative, and false negative, two of which are associated with correct classifications, and two of which are associated with incorrect classifications. Depending on the application, some types of errors might be more important than other types of errors, which is one reason why these metrics can be very useful. For example, if you misclassify a benign tumor as a malignant tumor, then this can be temporarily disturbing, but not nearly as grave an error as misclassifying a malignant tumor for a benign tumor. Regardless of the application, though, a confusion matrix is a very convenient way to get a visual summary of the performance of the model. And thankfully, there's a convenience function in TensorFlow that allows you to compute a confusion matrix by passing in the ground truth labels and the predicted labels, and then the return value from that function can be passed directly to the heat map function in Seaborn to produce the annotated plot below. So the first thing to notice here is that the ground truth for each class is plotted on the y-axis, and the predicted classes are plotted on the horizontal axis. The other thing to note is that the entries along the diagonal represent the correct classifications, and the off-diagonal entries represent the misclassifications. So now it's really easy to see that there's only one member from class 1 that was misclassified as class 0, and 13 members from class 0 that were misclassified as class 1. So this is actually the one diagnostic that we've covered here that is almost always produced when developing classification models. And notice that we did not require any extraction of the model weights to do this. We simply needed to use a convenience function that's available in TensorFlow. So that's all we wanted to cover in this video. Just to briefly summarize, we learned that the mathematical foundation for classification is very similar to regression, with the exception that we need to use the sigmoid activation function and also a different loss function, which is binary cross entropy. And so rather than the network producing a single number, it's now producing a score for each class, which can be mapped to a class label. And as we'll see later in this module, we're going to cover multinomial classification, which involves classification of more than two classes. And we'll study that in the context of classifying handwritten digits 0 through 9. So thanks so much, and we'll see you next time.